Okay, so let's take a look at an example of how we can apply that equation to calculate different parameters. So we know delta G is equal to delta H minus T delta S. And it says, according to the table we described above, our reaction will be spontaneous only at high temps if both the delta H and delta S are positive. So it tells us now for a reaction in which delta H is delta H is 199.5 kilojoules per mole, and delta S is 476 joules per Kelvin mole. Determine the temperature in Celsius above which the reaction is spontaneous. So what we can do, because we know that delta G is equal to 0 at equilibrium. So what we can do is set this whole thing to be equal to 0, and then we can solve for the temperature. So we have our delta H minus T delta S is equal to 0. So we have now temperature would be equal to what do we have here? Temperature would be equal to delta H over delta S, right? So we have our delta H and delta S that are in different units. Okay, so we have kilojoules, we have joules. You want to make sure and convert both of them to the same unit, so we can convert this delta S into kilojoules. So this just divided by 1,000, this ends up being 0.476 kilojoules per Kelvin mole. Okay, and then we stick it into our equation down here. So the temperature then would be equal to delta H, so 199.5 kilojoules per mole over 0.476 kilojoules per Kelvin mole. Kilojoules cancel, moles cancel. We have 1 over Kelvin. So that gives Kelvin as our temperature, which is 419. Okay, and then in order to convert it to Celsius, because we're asked for the Celsius temperature, we just subtract 273 from this, and that gives 146 degrees Celsius. So temperatures above 146 degrees Celsius then would be the range at which the reaction is spontaneous. Temperatures below that would be non-spontaneous. So we can use this equation. Obviously, if you have, or you can substitute delta H and delta S values in here to solve for delta G. The sign of delta G tells you the spontaneity of the equation, as long as you know the temperature. And again, the temperature has to be in Kelvin. Or in this case, we can use, and we can set this entire thing equal to 0 and solve for a particular temperature, the temperature above which a particular reaction is going to be spontaneous or non-spontaneous. Now, we talked about standard enthalpies of formation in the previous thermochemistry. Way back in Gen Chem 1, we talked about standard entropies earlier in this section. There's also standard Gibbs energy change, which is abbreviated delta G with that little degree sign. So this here is your standard conditions. And for standard state conditions for Gibbs free energy, we have the following that are defined. So gases for standard state are 1 atmosphere of pressure. Liquids would be a pure liquid, pure solids. The elements are defined as the most stable allotrope at 1 atmosphere and 25 degrees Celsius. And then for solutions, we have our 1 molar standard state condition. So these are important because we're defining these as the standard conditions for our Gibbs free energy. And these values, the delta G values, these are tabulated. So you can look these values up in your appendix, in the textbook. And you can find these. And it's the same type of a approach we're going to take to determine the delta G for a reaction. The delta G standard for a reaction is simply the sum of the delta G of the products minus the sum of the delta G for the reactants. Okay, so again, products minus reactants, final minus initial, because delta G here is also going to be a state function as well. So we can look these values up, like I said, in a table, and we can determine the delta G standard for a particular reaction. So let's take a look at an example. We have to calculate the standard Gibbs free energy changes for the following reactions at 25 degrees. So we have the combustion of methane and oxygen to produce CO2 and H2O. So the delta G for this reaction would be the delta G of the sum of the delta G of the product. So we have here the CO2. And again, pay attention to the stoichiometry. Plus 2 times the H2O in the liquid form. So that's our products minus the reactants. So the reactants here are CH4 plus 2 times that of O2. Okay, so we can look up these values from the appendix. The value for CO2, delta G of formation of CO2 is listed at negative 394.4 kilojoules per mole, plus 2 of the H2O liquids. H2O liquid is negative 237.2, minus the sum now of the reactants. So CH4 is, look that up, that's negative 50.8. And then for oxygen, because oxygen is an elemental form, an allotrope of oxygen, that's the most stable form for that, is going to be 0 kilojoules per mole. Okay, so we substitute these, and pay attention to the signs, by the way, because your delta G of formations, those are going to be important to keep track of, because you have lots of signs going on in here, and that's probably the most or the easiest place where you can get confused if you don't keep track of your signs. So the delta G, we plug those in, keep track of the signs. You see the delta G for this reaction is negative 818.0 kilojoules per mole. Negative delta G value means that this is going to be spontaneous at that temperature, which is, I think this is at 25 degrees. So we can determine the delta G standard for reaction by looking up the delta G of formation of the products and the reactants and substituting them. This is, the F here means formation, by the way. We can look these up in the appendix and substitute them in.